Hi, everybody. So, a couple of weeks ago, kind of just started to touch on this idea of chemistry. And so now we're really going to get started with our chemistry unit. And one of the questions I asked you back a couple of weeks ago when we first started talking about this is uh, do you see chemistry or its effects in everyday life? And if you do, then where is it? Well, as we go through this chemistry unit, every once in a while we're going to pause and talk about or watch a video about where we see chemistry in our everyday lives. So today, we're going to watch a video about where we see chemistry in our everyday lives. And in fact, we're going to take a look at where we see chemistry in cookies. So hold on, ladies and gentlemen, and we will go ahead and watch this TED Ed video about the chemistry of cookies.
In a time-lapse video, it looks like a monster coming alive. For a moment, it sits there innocuously. Then, ripples move across its surface. It bulges outwards, bursting with weird boils. It triples in volume. Its color darkens ominously, and its surface hardens into an alien topography of peaks and craters. Then the kitchen timer dings. Your cookie is ready. What happened inside that oven? Don't let the apron deceive you. Bakers are mad scientists. When you slide the pan into the oven, you're setting off a series of chemical reactions that transform one substance, dough, into another, cookies. When the dough reaches 92 degrees Fahrenheit, the butter inside melts, causing the dough to start spreading out. Butter is an emulsion, or mixture of two substances that don't want to stay together, in this case, water and fat, along with some dairy solids that help hold them together. As the butter melts, its trapped water is released, and as the cookie gets hotter, the water expands into steam. It pushes against the dough from the inside, trying to escape through the cookie walls, like Ridley Scott's chest-bursting alien. Your eggs may have been home to squirming salmonella bacteria. An estimated 142,000 Americans are infected this way each year. Though salmonella can live for weeks outside a living body and even survive freezing, 136 degrees is too hot for them. When your dough reaches that temperature, they die off. You'll live to test your fate with the bite of raw dough you sneak from your next batch. At 144 degrees, changes begin in the proteins, which come mostly from the eggs in your dough. Eggs are composed of dozens of different kinds of proteins, each sensitive to a different temperature. In an egg fresh from the hen, these proteins look like coiled up balls of string. When they're exposed to heat energy, the protein strings unfold and get tangled up with their neighbors. This linked structure makes the runny egg nearly solid, giving substance to squishy dough. Water boils away at 212 degrees, so like mud baking in the sun, your cookie gets dried out and it stiffens. Cracks spread across its surface. The steam that was bubbling inside evaporates, leaving behind airy pockets that make the cookie light and flaky. Helping this along is your leavening agent, sodium bicarbonate, or baking soda. The sodium bicarbonate reacts with acids in the dough to create carbon dioxide gas, which makes airy pockets in your cookie. Now it's nearly ready for a refreshing dunk in a cool glass of milk. One of science's tastiest reactions occurs at 310 degrees. This is the temperature for Maillard reactions. Maillard reactions result when proteins and sugars break down and rearrange themselves, forming ring-like structures, which reflect light in a way that gives foods like Thanksgiving turkey and hamburgers their distinctive, rich brown color. As this reaction occurs, it produces a range of flavor and aroma compounds, which also react with each other, forming even more complex tastes and smells. Caramelization is the last reaction to take place inside your cookie. Caramelization is what happens when sugar molecules break down under high heat, forming the sweet, nutty, and slightly bitter flavor compounds that define, well, caramel. And in fact, if your recipe calls for a 350-degree oven, it'll never happen, since caramelization starts at 356 degrees. If your ideal cookie is barely browned, like a Northeasterner on a beach vacation, you could have set your oven to 310 degrees. If you like your cookies to have a nice tan, crank up the heat. Caramelization continues up to 390 degrees. And here's another trick. You don't need that kitchen timer. Your nose is a sensitive scientific instrument. When you smell the nutty, toasty aromas of the Maillard reaction and caramelization, your cookies are ready. Grab your glass of milk, put your feet up, and reflect that science can be pretty sweet.
All right, so ladies and gentlemen, if I can get this video to continue on here. We'll see what happens. All right, so as I said, well, hopefully, let me just say first, I'm sorry if I made you a little hungry. Sorry I don't have some cookies for you today, but we're going to go back to talking about chemistry. And when we talked about chemistry a couple of weeks ago, I gave you a very simple definition that's going to be kind of our working definition to start with here in our chemistry unit. And that is that chemistry is the study of atoms and their interactions. So if chemistry is a study of atoms and their interactions, then it would probably stand to reason that we should begin by studying atoms and finding out what they are and how we know what they are. So we're going to start out by taking a look at atomic structure and also how we learned about the structure of an atom. It all starts back before the time of Christ, at about 400 BC in ancient Greece, with a gentleman by the name of Democritus. And Democritus was a Greek philosopher who not only did a lot of thinking and writing about government, which is where we get the idea of democracy from, but also just a lot of thinking about the world around him. And in doing so, he was the first person, at least that we're aware of, because he actually wrote down some of these things, he was the first person to really think about the fact that maybe there is a small particle that makes up all of the stuff that is in our universe. And he referred to that as an atmos, the Greek word atmos, which we now translate atoms. And so his idea that he came up with was that matter is composed of these tiny indivisible particles called atoms. So these tiny particles, they can't be divided down into smaller parts. And again, he called them atoms or atmos. He had absolutely no experimental evidence to go along with his ideas. These were simply his ponderings and thoughts and ideas. He had nothing to back it up, but amazingly, he came up with a pretty good idea. Now we're going to fast forward about 2,000 years or so to a gentleman by the name of John Dalton. If you want to think of this in terms of time of American history, I know for myself, I like to think of things in terms of that, even though he wasn't American. We're talking about early American history here. So from shortly after the Revolutionary War up until shortly before the start of the American Civil War. So this is the time that John Dalton was alive, a long time after Democritus. He was actually British, but he was a meteorologist. In other words, he studied weather. And in doing so, he did a lot of experiments, and so unlike Democritus, he actually had some proof of what he discovered. He took some of Democritus's ideas about these atoms, these small particles that perhaps made up everything, and through experiments was able to come up with a theory of his own. And his theory actually has 4 major points or postulates to it. So we're going to take a look at those 4 postulates now. The first one is that all elements are composed of indivisible particles called atoms. This is very similar to what Democritus said many, many years before John Dalton, although John was able to add a little bit to it. During John Dalton's time, Scientists did know that there were these substances called elements, things like oxygen, nitrogen, carbon. They didn't necessarily know the entire 118 elements that we know now. In fact, they definitely did not know about all 118 of them. However, they did know about several of them, and Dalton's theory was that these elements, oxygen, nitrogen, carbon, all of these different things, were composed of these tiny, indivisible, again, things that can't be broken apart, indivisible particles called atoms. The second part of his theory is that atoms of the same element are identical, and the atoms of any one element are different from those of another. So, for instance, let's take oxygen. John Dalton is arguing that all oxygen atoms are exactly the same. We could say the same for carbon. All carbon atoms are exactly the same. However, he's also saying that oxygen atoms and carbon atoms are not alike, that they are different from one another. And we could say this about any of the elements of the periodic table according to John Dalton. If you need to pause the video right now to finish writing this information, you may do so. The third part or postulate of Dalton's theory is that atoms of different elements mix or combine in whole number ratios. This goes back to his idea that these particles are indivisible, and so he believed that when oxygen combined with hydrogen to form water, that it had to do so in a whole number ratio. In other words, 2 hydrogen to 1 oxygen. You couldn't have, say, 3 hydrogen to 1.5 oxygen. Had to be whole numbers. The fourth part of his theory was that when chemical reactions do occur, the atoms are either separating or joining, or they're rearranging. And that when that happens, atoms of one element never change into another element. All right, so in other words, when oxygen reacts with another element, it's not going to change into a different element. The way it might join together with another element, it might separate from another element, or it might rearrange the way that it's joined with another element, but it's not going to actually change into another element. Oxygen, according to John Dalton's theory, is never going to become hydrogen. Carbon is never going to become aluminum. All right, so these are John Dalton's 4 postulates to his theory about atoms. Again, if you need to pause the video here to finish writing this information down, you may do so. So when we come back to chemistry tomorrow, we're going to take a look at yet another scientist. His name is J.J. Thomson, or Joseph John Thomson, as well as several others. We're going to take a look at some of their experiments that they did and some of the things that they discovered about atoms. We'll also take a look at whether or not John Dalton's 4 postulates were actually correct. So back in the mid-1800s, how correct was John Dalton in his ideas? How much did he really accurately discover about atoms? So we'll take a look at that over the next couple of days. For now, go ahead and put your notes in your binders. Have a good day, everyone.